Okay, our next speaker would be Professor Steve Zhu, who used to work in high energy physics and then moved gradually to important topics that has spectacular applications which influence modern science, modern technology. So we would have Steve. Where's the speaker? Oh, that's right.
Okay. Right. Thank you for those of you who want to depart from the most fundamental questions in physics, as exemplified by the two earlier spectacular talks. I'm going to go down to something pretty mundane, but really I also want to touch base with this audience and talk about things that possibly you can understand. So the main theme of this is that science doesn't always advance with a clear vision and a well-executed plan. As we just heard, the most exciting things in science are when you get surprises. And indeed, some things just happen by accident. So to give you an example, I show you my father and my mother and my father's oldest sister on their wedding night. Very distinguished family. My father's oldest sister was a full professor at Tsinghua University in chemistry before World War II. And she's been often recognized as the most significant women chemists in pre-war China. But after the Communist Revolution, she had to come to the United States. And being a woman, being Chinese, she couldn't get a job that equaled the distinction of Tsinghua University. So she could only get a job teaching at a small college meant to teach young ladies how to teach elementary and high school. Nevertheless, she was still a spectacular organic chemist, applied for an NIH grant in a place that didn't have any research. And for the next 25 years, she was funded by the National Institutes of Health, which paid in those days for this small college to establish a laboratory. So that was my aunt. My grandfather, Xu Tinli, went to Cornell as a graduate student in civil engineering. He came back and in just less than a decade became the president of his university at the age of 30 years old. After the revolution, he too had to leave, penniless, nothing, no job, no prospects of being a professor. So he had to reteach himself civil engineering, which he did, went into his business by himself. And by the time he was born in 1900, by the time he died in about 1990, just before, he received the highest award for the American Concrete Institute. So he had to start all over again, but still managed to survive. And then his older brother was a professor of physics at Peking University, also Academia Sinica. His thesis advisor was Perrin. Perrin got a Nobel Prize for his work on Brownian motion, which turns out intimately connected with my work. And as the French tradition, when someone gets a Nobel Prize and there's a graduate student who did the work, they also give him a medal. So he got this medal. So very, very distinguished family. How could they produce something like this? This is me. I want you to feel even more sorry for myself, for me rather. I come from not only a distinguished extended family, but I had two brothers. My oldest brother went to high school, set a record in the history of the high school for the highest cumulative average. He goes to Princeton, gets a Ph.D. in theoretical physics in MIT. And then after he realized it's very hard in the 70s to get a professorship in theoretical physics, high energy physics. So he went back to medical school, got an MD, Ph.D. He's now a professor at Stanford in biochemistry and oncology. My younger brother is the smartest of the three of us by far. He has 5 degrees, a PhD at 22. Even though he didn't graduate from high school, he just skipped his senior year. He was rebellious. But he talked his way into UCLA after a year. And he's the most famous and certainly the most expensive patent litigator in the United States. He's president of the board of overseers of Harvard, so on and so forth. So I was the first male child in my extended family not to go to Harvard or Princeton. So you should really feel sorry for me. But I went to the University of Rochester, which was actually a blessing. No one heard of my family, and I thrived there. I went to the University of California, Berkeley. At the time, had 9 active Nobel laureates in physics and chemistry, and that's where I spent my early years. And while I was at Berkeley, I began to notice it was, at that time, the greatest physics department in the world. And I learned that new instruments allow you to see new things with new eyes. And so I told myself, you know, if you're the 100th person to look under a rock, you're not going to find anything new unless you're exceptionally intelligent. But if you're the first person to overturn the rock with a new instrument, you don't even have to be smart to discover something. So my vision was, given my insecurity complex, not being smart, I will help build new instruments and maybe I can get lucky. There's if you step back and look at this, we always think of science as giving technology, but as you witnessed, especially in the last 2 talks, this actually goes the opposite way, that technology quite often leads to very new physics, and it's the pursuit of technological goals that have led to some of the most innovative science. And as I said before, new instruments allow you to discover new things. So when I was at Berkeley, as mentioned, I started life with Eugene Cummins. He was an expert in beta decay. And then while I was a student there, I was messing around with some failed experiments. And then quite suddenly, the Bouchiats published a paper that said, in a laboratory experiment, you can actually test the Weinberg-Slalom glass shell model. It required a very, very good laser, one you could not buy. And so that's me constructing this laser. It took me 5.5 years, 3 years, and plus 2.5 years more. 2 years as a postdoc and 3.5 years as a graduate student. It was pretty lackluster, but for whatever reason, I don't to this day fully understand, but they asked me to, the physics department at Berkeley asked me to apply. So I applied with a 3-sentence letter. Dear Professor, the chair of the department was Jeff Chu, a bootstrap theorist, and said, Dear Professor Chu, my advisor says I should apply to Berkeley. Can you consider this letter my application? And they hired me. But I hadn't published a single paper, so it was a little bit crazy. My graduate students and postdocs today assure me that could never happen today. But in any case, I worked with a beginning graduate student who was going to be my first graduate student. I get a startup package from Berkeley. I used it to buy lasers and off and running. So, but they said, since you spend all this time at Berkeley, we'll give you the opportunity to go somewhere else for a year or two, and then you can come back, but here's your startup money. You can start your group or you can go away. And I said, I'll take the money, I'll start my group, and I'll also go away. So where did I go? I went to Bell Labs. It was a spectacular place. 15 scientists, between 15 and 14 scientists got there, did work there that received Nobel Prizes. And so that was part of what was happening. And I'm not going to go through this, it's too long, but I had a lackluster couple of years at Bell Labs. But finally, I went to Bell Labs Homedale. I was asked to start a new basic research department in the sister lab at Homedale. This is what it looks like, and the water tower looks amazingly like a transistor. But in any case, while at Homedale, I started the work on the laser cooling and trapping of atoms. Now, how did I do this? Well, I was a department head, and a fellow department head was a fellow by the name of Art Eshkin, a truly brilliant pioneer physicist. And he had this dream of trapping atoms, but it started with trapping particles. For example, if you took a laser beam and put a little polystyrene sphere in a tank of water, if the particle went to the left, there would be higher intensity here, so it would be pushed over here. If the particle went to the right, it would be pushed over here. And so, yes, you can see the cursor. So in any case, that was great. He called this a dipole force, and you can analyze it in several ways. But one of the ways he analyzed it is if it was a macroscopic, several micron sized particle, you can actually think of it as a lens, and the asymmetry in the bending of the light rays, because the light was not uniform, would actually force the particle to go to the center. I prefer to think of it in a different way. And again, stepping back and saying, what was he really interested in? He was interested in holding on to neutral particles, but not by getting atomically close and touching it, so the atoms in your finger, the atoms in the marble, would actually get within angstroms of each other. He thought the following, that if you think about static electricity, you have a charged rod. It induces a dipole moment, a little separation of the positive and negative charges on this neutral particle, like a dielectric sphere or something. So this induced dipole moment, P, the energy goes as a minus P dot E. And so if you look at that, you find that this particle wants to go to a region of highest laser intensity. So the force is the gradient of the energy. All right. Now, it turns out, that if you, there's a theorem that says, can you arrange charges around some boundary so that you create an electric field maximum in a region where there is no material? And there's a theorem called Earnshaw's theorem that's impossible to make a static electric field. Now, when I heard about this, I said, well, I don't understand. Why is it called Earnshaw's theorem? Why isn't it just Maxwell's equations? And in Maxwell's equations, that's one of Maxwell's, the integral form of Maxwell's equations. And if the divergence of E in a region where there's no charge is equal to 0, that means, if my intuition about divergence is, if you have a sphere, the definition of divergence, you have a spherical surface, you look at all the flux lines going in, all the flux lines coming out, and you shrink the boundary to 0. So that's the real definition of divergence. And so flux lines going in and out are equal in number. So if the force is proportional to these flux lines, you couldn't actually trap a particle. Okay, so that's a much better way of looking at it, I thought. But you can violate Earnshaw's theorem because it's a theorem in static electricity. So if you focus the laser beam, you have an oscillating electric field that creates an electric field maximum. Okay, however, it was shown by Jim Gordon. Jim Gordon was a brilliant physicist at Homedale. He was the graduate student who worked with Charlie Townsend, the first maser. And he found that this mysterious dipole force, if you tune below or above resonance, it would switch signs. As I was beginning to get interested and asking Art and also John Bjorkum what's going on with that, and he said, oh, that's very complicated. Only Jim Gordon knows. But that's not true, because I was putzing along, and the way I work is, if I can't reduce the freshman sophomore physics, I feel a little bit stalled and refuse to go further. So everything I was doing was being reduced to freshman and sophomore physics. So consider a harmonic oscillator. The harmonic oscillator is the charge on an atom, and there's an absorption, and there's a phase response. And because of that, in phase, below resonance, you're in phase. Above resonance, you're out of phase. So if you're below resonance and you're in phase, think of that electric field as oscillating, but the charge on the particle, the induced charges on the particle are in step with that field. So it reduces to static electricity. And that's all it was. But if you go above resonance, then you know the response of harmonic oscillators, you're 180 degrees out of phase, so it flips sign. So all this was just freshman physics. And so that was good, took the mystery out. Okay, so then at the time, ions were being trapped, and after they were trapped, people were cooling them, Dave Wineland and his colleagues at National Bureau of Standards. And so the idea was trap an atom and maybe you can use light to cool it. And so the idea is very simple. Suppose there's an atom and it's moving to the right, and you shine a laser beam on it, and you shine another laser beam on it, and you play one simple trick. You tune the light so that it's below the natural resonance of this atom. And what happens is this atom is going towards this laser beam, and a Doppler shifts it into resonance. It's going away from this laser beam, so a Doppler shifts it out of resonance. Now consider the scattering of many, many photons, time average, and what you find is there's a force opposite its motion. And of course, if the atom goes to the left instead of the right, the Doppler shift just reverses and it looks like magic, it cools. So I got very excited by this. I wasn't really reading the literature. It's a fault I still have. And so I started doing this experiment, and within a year from the idea, I went to my director, Art Ashkin, and said, not Art Ashkin, I was the fellow department head, my director was Chuck Shank, and I said, this is really simple, it's gonna work. He looked at me, he had closed down the laser cooling effort of Art and his colleagues, but he said, okay, you can do this, but don't try to talk anyone else into wasting their time. You got positronium to work, you can waste your time. And so now, why didn't other people, for example, Hensch and Shallow, or others in the 10-year interval do this experiment? And they forgot one simple calculation. If you put this atom in this sea of counterpropagating laser beams, it creates a drag force. It's easy to show this. And if there's a drag force, but it's being buffeted on all sides by photons, there's a stochastic noise. So its analogy was like a Brownian particle. You got a little sphere, and it's being buffeted on all sides by Brownian motion, but it's got viscous drag. So I started to write a program and remembered my sophomore physics and said, I don't need to write a program. Einstein figured this all out. And lo and behold, if you put atoms in this soup, it would hang around for a second. So all of a sudden, that's what got me excited. And I said, this is so easy, it's really gonna work. Okay, now we got lasers cooled, optical molasses. The temperatures were very cold. They were about 1/4 of a thousandth of a degree above absolute zero, but I made a really bad mistake because it looked like it was actually less than 0.1 millikelvin. But I was so guided by theory, I convinced myself of some argument that said, well, you know, I've had big error bars. Anyway, lesson to the young people, don't be guided by theory. And anyway, but we had these cold atoms, 1 million of them in about a cubic centimeter. And yet it didn't look like we could trap them. We tried a few ideas. And of course, Ashkin had already suggested the simplest laser beam if you can focus in a very tight, small spot. But the trapping volume was about 10 to the minus 6 centimeters. So you get one atom. And one atom trapped out of 1 million atoms that are diffusing around is not going to make a great signal. And so what was going on? And so this simple focused laser beam trap was considered way impractical. And it took me a couple of weeks to realize, wait a minute, you can use random walk again. You've got an atom in a trap, and if it falls in, you oscillate between cooling and trapping, and it falls into the little potential. It's great, you got one atom. But there's Brownian motion around, and it's very rapid. And so there's all these other atoms that go to the boundary of the trap and also fall in. So you can easily convince yourself over a good fraction, a half a second, you can get thousands of atoms landing in the trap. And that's all it took. It took another random walk diffusion realization. So it worked. And that's me when I was younger, before the phase transition. Never mind, that's my phase transition. And Art Ashkin is staring at this apparatus. So the idea that you can have a single focus laser beam trapped in optical molasses, the molasses was like a fluid. And then the optical trap was this little potential well that atoms would fall into. And then during this time, Ashkin said, you know, this optical molasses, we can do a macroscopic experiment. Instead of optical molasses, you just use water. Instead of an atom, you use a bead, and you have a single focus laser beam. But you notice in 1970, he was very close to this. He had just 2 focus laser beams. And so why did it take 15 years to realize that if you put the little particle of water, the water would be the molasses, it would keep the particles cold, and it would have worked. Now, there's a huge difference between 2 focuses moving around like that and a single focus and moving a mirror. So when you have a single focus laser beam, you also had what we called an optical tweezer trap. And in the same year, we published the cooling of, a trapping rather, of atoms. Art Ashkin published a lensing system that he had an objective with high numerical aperture. This happened to be a water immersion objective, and he could actually trap particles. So this was very exciting. So one day he comes into my lab, and he's wide-eyed, and he says, Steve, you can't believe this. You got to come to my lab. I said, what? What happened? He says, I've discovered life. Okay, what do you mean? So I look in this apparatus with a Edmund Scientific really crappy telescope, and you see this little thing going around, and then he turns off the light, and it swims away. It's New Jersey water. There are bacteria in New Jersey water. And so it found out he could trap E. coli, and if he used infrared light, he can trap them, move them around at will. And in fact, he later showed you can have, for example, a yeast crawling along. Using the optical trap, you can reach inside, grab organelles, that's little thingies in the cell, it's a technical term biologists use, and you can actually pull this organelle down with the trap, let go, and it kind of springs back. It's kind of like an optical trap. We can reach in, grab your liver, pull it a little ways, let go of it, springs back. Anyway, this set off a great series of experiments by Art Ashkin, who later got a Nobel Prize, much later, for his work in biology, and which really led to the optical manipulation of molecules. The first optical manipulation of molecules was done by me when I got to Stanford, because I was inspired by Art Ashkin. I said, look, we can trap atoms, you can trap bacteria. Can you trap and hold on to individual molecules? And so I thought, well, if you glue little handles, polystyrene spheres, to this, you can do this. This is an example of a movie where you see a long piece of DNA lit by fluorescent dyes on the DNA. You hook this laser beam on a little joystick that tilts the mirror, and you can just play with the molecule. After a day or two, and then my graduate students were playing at night, to them it was a video game. I said, no, maybe we should do some serious science. But anyway, it led to a lot of interesting things. By the way, this is me when I was 40, arriving at Stanford. And one of the first things I did, besides the biology, was I said, you have really cold atoms. You can toss the atoms up, and they're so cold, they just go up ballistically and come back down and in a so-called atomic fountain. And even when I was a graduate student, I knew of a failed experiment at MIT The graduate student worked on it for many years. He had difficulty getting a Ph.D. He struggled because there was never any cold atoms that came up and come down, but the fast atoms would knock the cold ones out of the way. But he made out okay. This graduate student's name was Ray Weiss. And, but anyway, he never published this experiment until his Nobel lecture. But I knew about it from word of mouth. Because of this, I said, if you have cold atoms in a high vacuum, you toss them up, there are no fast atoms behind it. So they'll go up, they'll come down, and you can do precision microwave spectroscopy. So the first thing was you trap this. There's another trap called a magneto-optic trap that I don't want to talk about, also demonstrated by Bell Labs. You had a little fountain, goes up, it comes back down, and you do some radio frequency microwave spectroscopy, which was very quickly became the microwave hyperfine splitting, first of sodium, but then cesium. And so in a very, very short time, less than a decade, the atomic fountain, atomic clock became the standard of the world. And it's progressed since then, and Junyi at the University of Colorado Boulder and Gilla now has about 21, it's a little bit better than this, it's about 21 or 22 digits worth of precision in the energy level. That's a lot of precision. To give you a sense of it, the age of the universe, this is an old slide, maybe 13.5 billion years old, it's the number of seconds. And so if you started one of these clocks when the universe was born and asked how accurate it would be a couple hundred milliseconds. It's very good. You might ask, what are you doing? You don't need that precision in anything. Aren't you just showing off? And the answer is, of course. We're showing off. But it turns out that measurements of time and frequency shifts are the most accurate measurements in all of physics because we can count really well. And so counting, and now counting optical frequencies has now become a reality, another Nobel Prize. You have this great precision. And so these are some of the examples of what you can do with this great precision. Another thing we did when I was at Stanford is you take an atom and you have two counterpart beams of light that go to a virtual excited state back down to another ground state. So when you go up to the excited state, it absorbs a photon, the atom gets an impulse this way, and then this stimulates the atom back down in a virtual state, so you get another impulse the same way. So by making transitions between ground states, you can actually put photon momentum on the atom. Because it's a coherent process, you can make a coherent superposition of states. And over the years, many, many years, even beyond this, we can add just not 2 photon momentum, we can get 100 photon momentum. Make very, very precise so-called atom interferometers. These atom interferometers, first demonstrated by Mark Hesvich and myself in 1991-92, are now the most accurate way of measuring gravity by far. It's being used to test equivalence principle, and it's being used as the next generation gravity wave detectors to complement LIGO because it's in a different frequency spectrum. Okay, so then I go on and I was happily minding my own business, and I was asked by my former boss at Bell Labs, Chuck Shank, and also by Bert Richter, who was then director at SLAC, that Chuck is retiring from being a lab director for 15 years. Would I consider taking the job? I said, no, I'm very happy doing research. The last thing I want to be is a bureaucrat, with all due respect to deans and presidents out there. But they asked me again. I said, no, not really interested. But it says in the Bible you have to say no 3 times. And the third time, Chuck said, oh, look, just show up. And 4 years talking about climate change and how serious the problem might be. And here's this wonderful laboratory just above the University of California in Berkeley. Very distinguished laboratory. About 36 young scientists started their career there that got a Nobel Prize. So it's as distinguished as you can get. And when I was a graduate student, a postdoc, and a beginning professor there, I too was a member of Lawerence Berkeley Lab. So I said, all right, you can really leverage things if I go and give pep talks about how important it is to at least these brilliant scientists at least think about it. And if you think of something, you never tell anyone what to do. You just have to get them excited about the possibility. And I used to say, you know, this is a really important issue, but to whet your appetite, I'm sure that there will be Nobel Prizes given for solutions. I did not anticipate there were 2 so far: blue light emitting diode, the light efficient diode, and batteries. There will be at least another 2 or 3 for sure, solutions to this. I was concerned this is the global rise in temperature. I'll be talking about this 3 days from now, but it's getting very, it's rising very much. And just to remind you, the UN limit of 1.5 degrees, we are passing today. So we're beyond that. Where do I think we're gonna go? First, let me also tell you to whet your appetite so you can go to my talk on Wednesday. Most of the damage that we've done to climate is not visible. And the reason it's not visible is because the oceans are absorbing 90% of the heat, and the oceans are very cold. So it's like you have a glass full of ice cubes, and until you melt those ice cubes, it's gonna stay cold. What determines the weather is the surface temperature of the ocean and the surface temperature of the land. But because the bottoms of the ocean are very cold, close to 2 degrees centigrade, it's gonna take 50, maybe 100 years to warm up. So the damage we've already done is not visible. The weather we will get is not visible for 50 or 100 years. So if you think it's hot now, just wait. In any case, so here was my concern. Here we are. This is no policies. This is current policies, but not being enacted. And due to some, shall we say, backtracking by my president, other countries are similarly backtracking, and we are not going to be following current policies around the world. So we are heading to, best guess, 3 degrees, maybe 3.5 degrees above where we are. We're about 1.5 degrees now, but another 2 degrees. Okay. So for that reason, for whatever reason, I don't know, I didn't do politics, but when President-elect Obama in the 3rd week in November, I get a call and said the President-elect would like to meet you for a very important job. I said, I don't think I want to work for the government. I was thinking of stepping down as director. How important is this job? And they said, Secretary of Energy. So I said, okay, I'll fly to Chicago for that. The previous president, Bush II, wanted to know whether I was interested in being science advisor. I was not. Science advisor is an advisor. Being Secretary of Energy, you have budget authority. So I met with President-elect Obama. He's, you know, it's in his warm room. He's from Hawaii. He greets me and says, everybody says you should be the new Secretary of Energy. I say, who are these future former friends of mine? He ignored the joke. And for an hour we talked. And I was so impressed with him that I told my wife, Edward, how did it go? What are you going to, you know, I said, this guy's really impressive. If he asks me, I will say yes. We talked for an hour about where we stood on the issues. He said, I want 2 things in my term as President of the United States. 1 or 2 terms, whatever. He said, reform healthcare and do something about climate change. And those are the only things I really care about. So I was very excited by that. And so when I became Secretary of Energy, I used to quote a Sheikh Yamani, a former Saudi oil minister, and he said the Stone Age came to an end, but not for lack of stones. and the oil age will end, but not for lack of oil. Now, that's not have anything to do with why he was a former oil minister. He meant we transitioned to better solutions. And what he really meant was if we don't have better, which includes economically better as well as cleaner for the environment, the oil and gas is going to come out of the ground. And I think it's true. If you got trillions of dollars underneath the ground and you're a country that has that, there's a lot of political pressure to bring it out of the ground. All right, so now I was also, so part of my job was the cheerleader for the people, the National Lab scientists, also the employees at the Department of Energy. And I would say the greater danger, I was quoting someone, the greater danger for most of us lies not in setting our aim too high and falling short, but in setting our aim too low and achieving our mark. That was said by Michelangelo. All you young people out there, these are very wise words. Anyway, there was, some good, some bad. You get congressional hearings where they try to skewer you for doing something, making transitions to clean energy if they didn't believe in that. And then occasionally you get these blasphemous news articles. So one appeared in The Onion in February 2013, and it says, hungover energy secretary wakes up next to solar panel. Let me read you the byline. This is Washington. Sources have reported that following a long night carousing in a series of DC watering holes, Energy Secretary Stephen Chu awoke Thursday morning to find himself sleeping next to a giant solar panel he had met the previous evening. According to sources, Chu's encounter with this crystalline silicon solar receptor was his most regrettable dalliance since 2009, when an extended flame with a 90-foot wind turbine nearly ended his marriage. Anyway. So the press liaison at the Department of Energy looked at me, we smiled at each other. This deserves a response. Anyway, there was also some not so funny things. One of the things that happened in late April 2010 was the Deepwater Horizon, an oil exploration rig exploded, caught fire, drifted to ocean. It just drifted away by 45 degrees. It sank, the pipe snapped, and underneath the water, they had a TV camera that CNN was showing 24/7 oil and gas leaking out of this. And so there was tremendous pressure on the administration to do something about it. And President Obama's simple thing was, after a cabinet meeting a couple of days later, he just goes to him and says, Chu, go down there and help them stop that leak. Because he knew I was an active scientist. And so I said, okay. Figured I'd, ask a couple, 3 or 4 other people, they all said yes. They said, well, great. Or they said, I have to tell my department chair, maybe I can get relief of duty. I have to tell my spouse, things like that. But we all went there and met. And for the next 2.5 months, I was living half-time in Houston, helping them stop the leak. And literally after the first week, the people, BP, was the responsible company, the engineers and all the top brass decided we weren't going to talk to the press. I said to my little group, no one talks about anything. We're here just to stop the leak. And so they began to trust us. And in fact, we did help them stop the leak. I would fly back and other cabinet members would look at me and say, Steve, you look happy. How could you be happy in this stressful situation? I said, oh, I am happy. I'm helping solve a problem, technical problem. So this is what scientists do. They get happy when they solve technical problems. Anyway, so that's what happened. I returned to Stanford in the spring of 2013. Why did I only stay 4.25, 4.25 years? Well, it was my dear, lovely wife. She said, She looked at me and said, you know, Steve, no one's irreplaceable, not even you. I'm going back to California. I hope you join me. So I had to explain to the president, I'm sorry, I really would like to stay another 2, maybe even the full 8 years, but I think, you know, I got another boss. And, you know, so I said, okay. We talked. And so I go back to Stanford this spring. You know, I was a joint appointee at the University of California, Berkeley, and at Stanford. There was a difference. Berkeley kept my office, kept my lab space. They loaned it out, but they said, when you come back, we'll give it back to you. And whatever, and all your setup money you didn't spend. And Stanford said, after I went to DC, they took away my lab space. They took away all my discretionary money, and that was it. And that's why Stanford's richer than Berkeley. But my wife gave me no choice. She said, we're going back to Stanford. She was the dean of admissions at Stanford, had all her friends at Stanford, and said, no choice, we're going. So I had to explain to the president of the university and the provost, you know, it was very cute because 2 former secretaries, George Shultz, Secretary of State and Secretary of Commerce, and Bill Perry, Secretary of Defense, they called me up, they heard I was leaving and said, would you mind if we talk to the president of Stanford to say how important it is that Stanford get you back? I said, no problem. And they did. And so, but I told the president and the provost, your life is going to be very simple. There will be no counter bid. My wife has forbidden me to consider Berkeley. And I told this to the general counsel of the Department of Energy, and he looked at me dumbfounded and said, hasn't anyone told you how to negotiate anything? But I said, you know, if I get a new idea, will you help? He said, sure, we'll help. Okay, anyway. So there were some new ideas. I want to go briefly on this little cartoon of how people try to anthropomorphize biology at the molecular scale. So this is this cartoon of Kinesin walking, but it doesn't work like that. Erwin Schrödinger, in a series of lectures he gave in Ireland, Trinity College in Dublin in 1943, later put into a book called What is Life, which I read as an undergraduate and reread again and again. And he said something very profound. He said, from all that we've learned, in that book, he's predicted there's got to be some storage of information because that's the key to biology. Maybe it's stored on a linear polymer, i.e. DNA, you know, kind of a pure thought. That's how brilliant he was. But he also said, from all that we've learned about the structure of living matter, we must be prepared to find it working in a manner that cannot be reduced to the ordinary laws of physics, not because there's any new force, but because the construction is different from anything we've yet physically tested. So what is he talking about? So I translated this and it said, look, man-made machines work where friction is minimized. We use ball bearings, we use lubricants, and they have inertia, and they spin. But in the molecular world, it's entirely different. It's embedded in viscous fluid. There are thermal fluctuations that dominate. So if Newton were the size of a bacteria but had the brain of Newton, his laws of motion would be very different. An object in motion would quickly come to rest. That means F is not proportional to acceleration. F is proportional to a drag force and velocity. And there's Brownian motion. And just how living organisms can survive and operate in this very dissipative, jiggly world is the subject of my July 15th talk. I will skip some of this and just go on to ending. So there's some time for questions. We're going to go over 550 parts per million CO2. We emit, including methane and nitrous oxide, the equivalent, and other things, we emit the equivalent of maybe 50 billion tons of CO2. Because we can't get the greenhouse gas emissions out of agriculture for at least a couple of decades, we don't have the technology to replace fertilizer. Just the using of fertilizer, not the energy of fertilizer, putting fertilizer in the ground and not absorbed by plants results in N2O emissions, which is 300 times worse greenhouse gas in the last 100 years. So you got to get rid of fertilizer, but we don't know how. And so, so we're going to need carbon capture, and at least the scale 10 or 20 billion tons a year. And by comparison, all of the landfill in the earth is only 2 billion tons. But you put CO2 under the ground, it's a much lower density. So we're talking factor 30 or 40 more stuff going into the ground than all of landfill. In fact, not surprisingly, it's comparable to all the stuff we take out of the ground in fossil fuel. It's got to be. It's actually a little more because carbon dioxide is a little more massive. When I was Secretary of Energy, I funded a carbon capture pilot plant. It cost $1 billion. The footprint is 1 acre. This is the size of a very large American-style pickup truck, and it required about 30% of the power output from a fraction of a coal plant, 1/4 of a coal plant, $1 billion. This is not meant for wide-scale deployment. It's not going to be deployed, that technology of using amines. And so I'm going to briefly mention that we may have stumbled on a new way of capturing CO2. This is Sang-Chul Kim, a postdoc who is now just taking a faculty position at NUS in Singapore. And what happens is when you expose carbon dioxide to water, very high pH, high alkaline water, the solubility of the carbon dioxide asymptotes to about 0.5 mole per liter, which is a lot. Gas at STP, standard temperature and pressure, is 22 liters. So it was well known to do that, and the only commercial carbon capture actually is using high alkaline water, but once they get it in the water, they have to heat it up. And it's the heating up that makes it very energy intensive and very energy costly. So we thought we could use electrochemistry, and we got very excited that we could shift the pH in electrochemistry with far less energy than we thought possible. It's certainly been demonstrated. This is what the thing looks like. But I'm here to tell you that, and we submitted the paper to Nature. It got accepted with some reviews, but before I told my group, I said, look, there's some problems with the paper, so let's investigate it. Let's not wait for the referees to find it. And what we found was our interpretation was completely wrong. The referees didn't find it. So we're going to have a very interesting reply to the editor because it's completely wrong, but we learned how to fix it. Maybe, okay? So, so I've never been in a position to try to talk my way out of a Nature publication, but, and then, in the same breath, talk my way back into it. The model we had was this molecule. It's a reduction oxidation molecule, very inexpensive, one of the cheapest organic molecules you can buy, called TEMPO, TMPO, which is considered for radix reduction batteries. This is our cartoon of a water being polarized by this charge here. And if you consider a reaction that takes a proton, combines with bicarbonate, makes carbonic acid, and finally CO2, that when you use up protons, we thought that this would readily donate a proton. That turns out to be completely wrong. There are two parts. We have an electrochemical part that turns this molecule from neutral to charged. But when it turns charged, it's not because of an electrostatic energy that does this. It has to do with very subtle chemistry with this nitrile group, nitrogen and oxygen, and splitting OH, H2O into OH minus. And so I don't want to go into it, but there's this thing called a side reaction. So here's our molecule. We oxidize it, then it's charged. We thought this charged molecule would be polarizing things. It doesn't. But we also found that it self-discharged and went back. That's a problem because it takes energy to oxidize the molecule. But on the way back, if it grabs the electron back, you recover it. So it looks like we could recover all the energy, but for this self-discharge reaction, we now understand this. We think we have a solution, remains to be seen. I'm not going to go into this, but I just want to conclude, leave 10 minutes, is that I do feel like an E. coli. Now, I learned about E. coli from Ed Purcell, who invented NMR and did the first scanning of the hydrogen clouds in our galaxy. And he said that this thing will swim, and it's too small, so it swims and it measures changes by its motion of it's going for food. So these things want to eat food, and then they split. And so it will go swim, tumble around and swim again. If it feels the gradient is going towards food, it keeps on going. But if it doesn't see any gradient, it doesn't stop and just sit there waiting for a signal. It just continues to swim. So it's like the perfect graduate student. You always swim towards progress, but even if you don't feel that you're making progress, keep on swimming. Anyway, that's this random walk of E. coli, and that's my life. Thank you.
Well, thank you. It's a fascinating story, which we should learn. So, any questions from the floor? Yeah. There.
Thank you so much for this wonderful journey. I was wondering, since you have been part of, like the government as the Secretary of Energy, but also for private institutions like the Bell Labs, as well as universities, I was wondering, since you're tackling such a huge issue such as climate change, what is policy-wise, or like maybe even like a moonshot-wise, like the bottleneck, and how can you best approach this problem? Is it scalability? Is it basic science? Is it all of that, or what is currently the status of that?
Yeah, great question. When I left the department, I went around started to talk to rich people to say what we really need is roughly akin to a Manhattan Project, but a Bell Labs for energy. Okay, in Manhattan Project, you're single use, you don't care about money, you don't care about anything, you want to make a really expensive bomb because you're at war. This is different. The solution has to be economically viable, and so you need something that makes economic sense. Remember Sheikh Ahmadi, it's got to make economic sense, but it's going to be basic research, it's going to be applied research, it's going to be all of the above. And I said, we need a Bell Labs for energy. And I was told, nah, rich people give to their alma maters, but they may not give to this, by a couple of rich people. So I gave up. I still think we need a Bell Labs for energy. Now, whether the US government's going to, well, it may not for the next three and three-quarter years, but but eventually I would hope that the US government, the European government, the Chinese government, all these people, because this is something, even though there's going to be valuable intellectual property, it's too an important problem. And we need the best minds rowing together.
Thank you so much.
Yeah. Second.
Thank you for giving me the opportunity. I'm not a scientist. I'm a historian of science and technology. And as a Chinese, I'm quite proud that you and Professor Samuel Ting are separately the fifth and the third Chinese American who got the Nobel Prize. So I wonder, how do you think of the traditional Chinese culture and family cultures on the steps to your success in science? And
well, as you know, the Chinese put a huge value in education in general throughout all of society. My family was a personal extreme of that. I was told when I was like in the second grade, my father said, Stephen, don't get married until you get your PhD. It was assumed that we get a PhD in science. And so, by the way, you younger people have kids, don't do that to your kids. Let them do what they want to do, encourage them. But But I think the tradition and the seriousness of education and the fact that it is considered really to be a scholar is one of the, when I was growing up, to be a scholar was the highest achievement you can be. Not a head of a company, not making a lot of money, not being the boss of anything, being a scholar. And I was told that. I still believe that. Which is why I didn't want to take any bureaucratic job. But sometimes one is willing to take a bureaucratic job because it actually gives you leverage if you can inspire people to go in this direction. But the short answer to your question is very much in my blood, in my DNA as a Chinese American.
Okay, thanks. Other questions? Yeah.
Somewhere back there, I can't tell. Oh.
So thanks for the talk. It's very inspiring. But I think you are very modest in calling it random walk, random changes. I think in my mind, and maybe you can reflect on it, doing science and looking at science doesn't matter what you do, what your discipline is, what you want to advance, and what you are curious about. It requires two kinds of being smart. You have to be academically, scholarly, curious-wise smart, but you also have to be street smart. And the street smart is the moves that you probably try to make. And actually, I think you were guided by street smartness, and then you got these things. So I'm kind of confronting your assumption that it's random. It's not really random, in my mind.
Okay.
You are being modest, of course, saying, "Oh, I was just walking there. I drank wine and I moved left and right." No. I think it's street smartness. Can you reflect on this?
Well, okay. So I have wide-ranging curiosity, but I would not know very much about anything. And so what I found was that, piqued by this curiosity, then I start to dig. And for example, in the curiosity about climate change, First, I started digging. I wasn't going to talk about climate change until I really understood the literature. And I started teaching classes on the physics of climate change so that I became an expert, so I wouldn't just spout off like, a Nobel laureate. And what Sam Ting said was very wise advice. He said, you don't talk about things you don't understand, but that doesn't prevent you from actually getting very deeply into an understanding. So this wide-ranging, a little bit, oh, that looks interesting, scratch a little, dig a little. Oh, and then the next thing I would do before spending a lot of time, I'd go find some expert and say, I'm thinking of doing this. Is this stupid, crazy? Sometimes they said, nah, it's great, except it's done 5 years ago. Other times, nah, it's not going to work because of this, and we'd haggle about it. And maybe 5 or 10% of the time, said, yeah, sounds like a good idea. Try it. So I didn't waste a lot of time in the library. I talked to people immediately. I got in the habit of doing that when I was a graduate student postdoc, and really got good at it at Bell Laboratories because there's so many experts walking around. And so again, my advice to young people, do it that way. Don't hide in a library, or now you don't, you chat GPT it. But if you chat GPT it, don't believe much of what it says. Use it as a pre-Google, but eventually go and talk to an expert before you read a lot of papers. Then you can have really targeted reading.
Any other questions maybe from students?
Very bashful students. No? Okay.
Okay, if not, let's thank the speaker. Great talk.
Thank you.